So, good morning and a warm welcome to this course on digital signal processing and its applications. This course is treated as a basic course, by and large, a basic course at the graduate level. However, that means for students who pursue a master's or a doctoral program. Typically, it's a core course for many specializations, or at least a course which occupies the status of an introductory or first level course on digital signal processing. The course is entitled Digital Signal Processing and its Applications. And before we proceed, let me introduce myself. My name is Vikram M. Gadre. I am a faculty member in the Department of Electrical Engineering, IIT Bombay. I have been instructing this course before a number of times. And what I intend to do right now is to first give you a feel of what we intend to do in this course. What is the aim? What is the objective of this course? What does the title mean? What lies behind the title? Not so obvious. And how we are going to conduct this course. Well, if you ask me to summarize the aims and objectives of this course in a few sentences, the first objective is to move from continuous independent variable to discrete independent variable. What that means is, if we take the example of an audio signal. In an audio signal, the independent variable is time. Right? So in fact, let's make it a practice to write down. So let's take an audio signal as an example. Independent variable is time. And the dependent variable could be depending on the nature of the recording. So it could be, for example, a magnetic signal if it is an audio magnetic recording, or it could be a voltage signal, whatever, right? So could be voltage, current, magnetic field, whatever. It depends on the nature of the recording, isn't it? Now, any meaningful signal, most of the signals, in fact, that we deal with, real life, have a continuous independent variable and a continuous dependent variable. By continuous, I mean, if you take any two values of the independent variable, you can always find a possible value in between them, no matter how close. So for example, if you take the values of time equal to 1 and 1.00001, I can still find the value 1.000005, which is in between these. So no matter how close I have my two independent variables, I am always able to find another value of the independent variable in between them. That is what continuity means. That's what is meant by a continuum. So we introduce this idea of a continuum, formally the idea of a continuum. A set where one has a distance notion. No matter how small distance between two elements. There is another with a smaller distance. From both. I told you this is an introductory course at the graduate level, isn't it? So when we introduce ideas at the graduate level, at the level of masters and doctorate, we are a little more formal, or we are a little more in depth than we are an undergraduate level, right? So we proceed from intuition to a reasonable level of completeness, not very rigid, not very rigorous, but a reasonable level of completeness. That shall be our practice. So even here, if you notice, we have not confined ourselves only to one-dimensional signals. In a one-dimensional signal like audio, of course, the independent variable is time. So in the real axis is what can be used to index time, right? And therefore the idea of distance is very clear. On the real axis, pick any 2 points. The difference between them, the modulus of the difference between them is the distance. And in that context, this definition becomes very clear. No matter how small the distance between 2 points, I can always find another point which is at a smaller distance from both of them. Both of them is critical. Okay? But you must remember that you can also have a two-dimensional independent variable. For example, you can have a picture. So we should make a note of that. Continuum would be more than one dimension. One dimensional, an example is time. 1D space, that is a line, and so on. It could be two-dimensional. So, for example, you can have a picture frame, you can call it if you like. So, the space on what you put a picture, on which you put a picture, is a two-dimensional continuum. In fact, it can be three-dimensional. So, all of us exist in three-dimensional space. In fact, now it is better known that we have more than 3 dimensions, but that's a different issue. We definitely know we are at least 3-dimensional. So, continua can be more than 2 dimensions, more than 1 dimension. It could be 2 dimension, 3 dimension, in fact multi-dimension. And what is important is that in most cases of real life situations, both the independent variable and the dependent variable are continua. That's what we must take into account. Many real life situations, independent variable, dependent variable. Both variables are continuous. Now, if you wish to capture the essence of what we are going to do in this course, we wish to be able to develop the ability to take such a real life signal, to take an equivalent signal or an equivalent entity where the independent variable has been discretized, but the dependent variable still remains continuous. Okay, so let's summarize that. In this course, we want to deal with them by an equivalent signal, where the independent variable is discrete. But the dependent variable is continuous. That's a deep idea. You see, we are not sacrificing the continuity of the dependent variable. We are only sacrificing the continuity of the independent variable. For example, if I have an audio signal, what I am saying is, I will understand as if I am going to deal with values of the audio signal taken at certain chosen instants of time. And when I say equivalent, what I mean is that I should choose my instance of time. I should choose the points at which I record the values carefully and strategically, so that I have no loss of information. I have nothing to lose by working only with those values and not the whole signal as it is. But I am not compromising in principle or in thought on the continuity of the dependent variable. So suppose the audio signal has been recorded in the form of a voltage waveform, or if it's a magnetic field variation, I am assuming that variation will be continuous. I am assuming that voltage waveform would be continuous, right? Although I agree that in practice that may not be true. In practice, that may also get discretized. That may also acquire only a finite set of values, because you may have finite precision, right? But we will ignore that. And there's a good reason why we are going to ignore it. If we were studying this subject about 20 years ago, we would have been very concerned about how we are going to record continuous values. But today, with the advent of very superior memories and very superior recording devices, that is almost a non-issue. One can record values very, very accurately to such a precision that one need not even worry about the fact that it is discrete. And that's exactly what we are going to do. Okay? At least to simplify matters to begin with. Now, of course, what do you mean by a variable being discrete? It means it disobeys that property of continuous or continuum. That means it is possible to find two values that you have chosen for the variable between which there is none. Right? And in fact, when you say discrete, actually it means this is true for every such value that you can find. For every value that you take, which you are accepting of the independent variable. That means, for example, if you have sampled in time, then for every value of time that you have taken, there are several values. In fact, you will not be able to find values less than a certain distance from that point. There is something like the nearest sample from there, isn't it? The nearest point in time close to that point, and therefore you will not be able to find values at a distance less than that from that point. Anyway, now naturally, why do we want to do this? The reason is very simple. That is exactly what you need to do if you want to deal with signals on modern computing devices. So what do we want to do? Ultimately, you see, we want to deal with signals. We want to make sense out of them. We want to modify them. So let's put down what we mean by signal processing. We understand what we mean by a signal. In fact, if you ask me, a signal is hardly different from any function of an independent variable. The variation of a dependent variable against an independent variable is a signal. As simple as that. It could be the variation of a voltage waveform against time. It could be the variation of a current waveform against time. It could be the variation of temperature across space. It could be the variation of intensity on a two-dimensional frame, as the picture does. It could be three different color variations giving you a color picture. So the variation of the dependent variable against the independent variable is a signal. And as we have seen, the dependent variable and the independent variable could either be discrete or continuous. We shall be dealing with potentially continuous independent variables, but which have been discretized. And now we will explain what we want to do. What do you mean by signal processing? So you understand what is a signal. What is meant by signal processing? Again, to cut a long story short, signal processing means two things. Essentially, modification and separation. At least from our point of view, it means two things. So, modification means I have one signal with certain characteristics. I wish to modify it into another signal with some different characteristics. What are those characteristics? That will take us some time to understand. Now I'll again give you an example, and we shall build on that example in the next lecture. Not only in the next lecture, in many subsequent lectures after. It will take us quite some time to build on this example. In the audio domain, taking again the context of audio, let us say we have a mixture of male and female voices recorded in an audience. Typically, male voices are likely to have what is called a lower pitch. They seem to sound slightly deeper. And female voices are slightly likely to have a higher pitch. It's likely to sound a little more shrill than the male voice. Is that right? Now, this is how we understand it intuitively. This is how we describe the two components of that signal, recorded signal, as we understand it or as we perceive it with our senses. But we need to go to a different way of description when we want to do something with the audio signal. This description is not going to help us process that audio signal. What do you mean by processing? We may either want to modify it. That means I want to take that recorded signal which has both male and female components. I want to suppress the male component and enhance the female component, or I may want to suppress the female component and enhance the male component of recording. That's an example of modification. Or I might want to separate. So I might want to have one signal essentially only of the male component or largely only of the male component, because you can't get exactly that, and the other signal essentially only of the female component or largely only of the female component. So I may want to separate or I may want to modify. Now it's easy to put down this description in common language as we have done. But to achieve this requires many steps. And as I told you, we are going to spend many steps in going there. We first need to translate what we have said into language that will help us build a system which will do what we want to. So if you want to build a system which will do this, it first requires translation of this requirement or of this description into a language which that system can understand. And that will take us several lectures. In fact, in a way, it will take us half this course. So it's a fairly heavy price that we pay if we wish to automate. But it's a price worthwhile to be paid. Because once we automate, we get several powers through the process of automation. So it's worth paying that price. To evolve a language, to evolve a platform where we can translate this common parlance into something that a system that does what we want to can understand. Now, what do we need for that? We need to first build certain notions of systems themselves, to build certain different ways of describing signals or to identify certain typical signals, and then to build certain domains in which we can characterize that system. And finally, to put down certain properties of a class of systems that we wish to deal with. All this we need to do. And of course, we'll need several lectures for that. Right? Is that right? So in the subsequent lectures from now, we shall be carrying out this task step by step. Is that right?